Hi, my name is Pratyush Pandey and today I'll be presenting my final year project, Distributed Task Offloading in a Multi-Tier Cloud Architecture. Let's look at the background. So in the figure you can see the multi-tier cloud architecture, which primarily comprises three tiers. Tier 1 is occupied by remote cloud data centers, which have very high computational power, whereas the latency is also very high because they are located remotely from the end devices. The tier 2 is occupied by edge devices which have lower computational power but they are located much closer to the end users, hence this decreases the latency. Finally, the last tier is occupied by the end devices like laptops, mobile phones, smart home systems, and other applications that leverage cloud technologies. This complex multi-tier cloud architecture has given rise to a huge number of applications being deployed on the cloud servers. In 2014, the aggregate server traffic at Google data centers rose almost 50 times. This was published in a research paper which is called Jupiter Rising, a decade of cloud topologies. However, such a rise in heterogeneous applications has already made an existing problem much more challenging. That problem is the efficient resource allocation at cloud servers and the offloading of applications or tasks in that infrastructure. The current literature proposes two different kinds of solutions, centralized solutions and distributed solutions. Centralized solutions are quite simple as they leverage a single master server to run the entire algorithm. However, the master server requires significant computation and this entire algorithm is prone to failure or crashes because the master server can crash and this will run down the entire system. Whereas distributed solutions actually distribute the computation of the algorithm across several hosts, and the hosts gradually agree upon a single solution at the end of the algorithm. This has significantly less computation, however, there is very high communication overhead due to exchange of messages. An example of centralized solution was proposed in the paper mentioned in the slide. The authors actually formulate the problem as a multidimensional knapsack problem, which is NP-hard, and then they provide an ant colony optimization based algorithm to the problem. Ant colony optimization, or famously referred to as the ACO algorithm, is very intuitive because it is inspired by the real life of ant colonies. Ants traverse down several trails and then they deposit their pheromones. The trails with the highest pheromone deposits are actually traversed by most of the ants in the colony. These centralized solutions actually lead to a very serious research gap in current literature. There is a lack of distributed solutions that account for time-sensitive applications like autonomous vehicles. Hence, during the course of my project, I'll be implementing such a deadline-constrained distributed algorithm, which is inspired by the ACO algorithm previously described. I'll also update the system architecture to accommodate the distributed algorithm, and I'll also simulate the distributed algorithm in a multi-tier cloud infrastructure, which actually emulates an asynchronous distributed environment. Moving on to the methodology. So the proposed distributed algorithm can be elucidated in the mentioned diagram. It primarily comprises of three phases. The first phase is the search phase, where we run the ACO algorithm multiple times on several hosts. When we finish running the ACO algorithm, these hosts actually exchange pheromone messages, where they pass down their pheromone matrix to other hosts, and then the search space is accordingly updated and the ACO is again run for a few other iterations. When the host has completed the max iterations, the host moves to a transition phase where the proposed algorithm actually allows the host to exchange done messages, and the done message basically implies that the host is done with the search phase. Once all the hosts have received a done message from every other host, then we move into the agreement phase, which basically involves all the hosts to agree upon a single solution by choosing the best solution out of all the sent solutions. As a part of the new system architecture, we deploy new offloading servers into the second tier, which is the edge tier. These offloading servers are task routers that help us run the algorithm. They also help us offload the load or task load onto different servers. They maintain global information about the network, which is like the resource constraints of different servers and the load crashes or failures in the topology. And they also operate in network subgraphs, which allows them to demarcate the entire network into several subgraphs, and these subgraphs serve as directories for different offloading servers. The simulation environment is an asynchronous distributed test environment. There are several parameters like the number of tasks, number of hosts, but the most important one is HP underscore random. It is a Boolean flag to randomize hyperparameters alpha and beta for ant colony optimization. The alpha and beta values are set to 1 each if the Boolean flag is set to false. If it is set to true, then we choose it from a random distribution with certain max and min values. The assumptions of the simulation environment is that it's asynchronous in nature. This is because we want to emulate the real life behavior of cloud computing systems. There are no node failures and there are no link failures, which is we have reliable communication channels. This allows us to only focus on evaluating the performance of our algorithm and not to manage any node failure or link failure in the system. Overall, the results shown by the algorithm were quite promising. As you can see in figure 8, the bar graph is basically demonstrating the average profits earned across different tasks. And the blue graph is for the centralized algorithm or the centralized benchmark. The red and yellow graphs are for the distributed algorithm with HP underscore random set to false and true respectively. As you can see, when HP underscore random is set to true, the distributed ACO achieves similar results to that of centralized ACO. When HP underscore random is set to false, it achieves slightly worse results, but then again comparative to that of centralized ACO. And increasing the arrival rate does not worsen the performance of both the algorithms. This ensures that our distributed algorithm is resilient to the arrival rate of tasks. Moving on to the time taken by the algorithm. So we show a box plot of showing time taken difference earned across different number of tasks. So time taken difference is basically subtracting the time taken by the distributed algorithm from that of the centralized ACO. So when there's a negative time difference, that ensures that the distributed ACO runs faster. Hence, we can notice that when HP underscore random is set to true, the time speedout ranges from somewhere from 15% to 42%, and when it is set to false, it ranges from 17% to 44%. We should also note that the speedup is highly underestimated because our experiment environment sequentially emulates the actual distributed system. Hence, the time speed up would be much more massive in a parallelized distributed environment. Moving on to the conclusion, our proposed algorithm has been able to achieve similar profits to that of the centralized benchmark. At the same time, it also offers a significant time speed up ranging from 15% to 42%. And also, our algorithm is quite resilient in nature because it does not worsen the performance when we change or increase the arrival rate of tasks to a huge number. Hence, this shows that the distributed task offloading algorithm that was proposed during the F5B project would be really helpful to scale the current increasing application workload on our cloud computing architecture. Finally, as a part of future work, I would like to parallelize the simulation in the test environment. This is so as to accurately judge the time speed up in different cases. And also, as a part of future work, researchers could expand the scope of the problem and look at make span minimization and try to reduce the energy consumptions at the end devices like smartphones and laptops. This slide is basically